the crystal field splitting in octahedral complexes. Before going for the octahedral splitting, let's see how the octahedral structure will look like. This is the octahedral structure. So at the center, the metal atom will be there. The metal ion will be there. And to that, all these points are the ligands. The ligands will be in this way, they are arranged, and at the center, the metal atom will be there. So in a cube, if you consider all these will approach through the axis, not through the corners of the cube. Try to draw the square here. When we draw a cube here, see, these are approaching through the axis, not through the corners. And even these two will go through the downside and upside corner or axis of the cube. So that is the reason in octahedral, the EG group, the axial orbitals will exert the more energy from the ligands. So the splitting will be done in such a way that the EG group, the axial orbitals of the d orbitals will show the higher energy level than the T2G. This is quite reverse of the tetrahedral complexes. In a tetrahedral complex, we have seen the T2G group will exert the more energy because through the complex, through the geometry of the tetrahedral, the non-axial places are the approaching points for the ligands. So here consider the d orbitals, the free state. Then the energy is increased, the average energy of d orbitals in a spherical field. Then the splitting will be done in this way. This is the increasing energy, and this is the barycenter or average energy. So this is T2G group and this is EG group. So the axial orbitals, that is dz square and dx square minus y square, will exert more energy or more electrostatic force from the ligands. So that is the reason they will show the higher energy level. And this dxy, dyz and dzx will show lesser energy because the ligands are not approaching by this non-axial plane. So now we will see how the splitting will be done with respect to the spectrochemical series, that is weak field energy, weak field ligands and strong field ligands, how they are splitting the d orbitals we will see now. Okay. See, you can see this for the D1, when the d orbital, for the D1, that is the example titanium plus 3 ion with the high spin complexes, that is strong field. High spin means that is strong field ligands. This is low spin means weak field ligands. So the splitting will be done in octahedral in such a way that when titanium plus 3 is being taken, the T2G will be filled with the 1 electron. That is the energy associated, the crystal field stabilization energy associated with this particular electron is minus 2 by 5 delta. So here crystal field splitting, in this crystal field splitting, here the energy difference, here it is 2 by 5 delta O and this is 3 by 5 delta O. The delta O means crystal field stabilization energy of octahedral complex. The O indicates the octahedral complex. Now we will see how the crystal field splitting is been done for the various electronic configuration of d orbitals. Okay, when the D1 is present, that is, let's take here the example of titanium plus 3. When the titanium plus 3, d orbital will bear only one electron, and the splitting will be done in this way. T2g being a lower energy level, T2g lower energy level, the electron will be filled here first. Okay, and same case with the weak field ligands, that is high spin. Then the D2, when the d orbital has 2 electrons, then the splitting will be done in this way, that is the titanium plus 2 and the vanadium plus 3. When these two are there, then the splitting will be done almost the same for the weak field and strong field ligands. And D3, with the D3, it is also the same, and the examples here are vanadium plus 2 and chromium plus 3. These ions will split in the same way even for the strong field ligands and the weak field ligands. And here the 12 dq, the delta q. See, this is the energy level which is coming for the 2 by 5. This is 4 by 5. Okay, 2 by 5 means it is 0.4. I'll write here, it is 2 by 4, 2 by 5, that is 0.4 of delta O. Okay, the delta O is written in the dq form by simply removing the decimals, that is multiplied by the 10. So here it is 4 by 5 and here 12. It is 6 by 5. That is 1.2. Okay, in this way all are written. So for the D4 electronic configuration, the T2G4 will split in a different way with the strong field ligand and with the weak field ligand, because D24 in the strong field ligand, the energy gap between T2G to Eg will be very high, so the electrons will be filled here itself. Okay, but whereas in case of weak field ligands, the energy gap will be maintained in such a way, so the electrons will be filled accordingly. That means all are half filled. Then for the strong field ligands, the T2G, the D5 T2G will be filled in this way. The T2G will be filled with the 5 electrons, but whereas here T2G will be half filled and Eg also half filled. So here the number of unpaired electrons will be 5. Here the number of unpaired electrons for each and every time, it is 1, it is 2, it is 2, it is 3, it is 3. Here it is 2, here it is 4. Here the number of unpaired electrons is 1, here the number of unpaired electrons is 5. Again, here if you consider the number of unpaired electrons are for the D6 electronic configuration is 0. And for the number of unpaired electrons in the weak field ligand is T2G 4 and Eg2. That means 4. Okay, so here the number of unpaired electrons will become 1, and here the number of unpaired electrons will become 3 again. Here the number of unpaired electrons when the D8 configuration, that is T2G, will be completely filled and Eg will be half filled. So it will be 2. So number of unpaired electrons here is also 2. Number of unpaired electrons in D9 electronic configuration will be 1, and here also it is 1. So here the number of unpaired electrons is 0, and here the number of unpaired electrons is 0. Accordingly, you can check now. We can see how the crystal field stabilization energy is related with the number of unpaired electrons. So if the unpaired electron is 1, then the crystal field stabilization energy is 4 dq. 2, it is 8 dq. 3, it is 12 dq. It is 2, it will become 16, and here it will become 6 dq. Okay, so for the D5 electronic configuration, it is 1 and it is 5. Likewise, all the strong field and the weak field energy levels with the number of unpaired electrons is being shown. Now we will see the examples of the D3, D4, D5 configuration. D4 electronic configuration, it is chromium plus 2 it is manganese plus 3, manganese plus 2, then iron plus 3. Here it is D6, iron plus 2, cobalt plus 3. For the D7, cobalt plus 2 and nickel plus 3. D8, nickel plus 2, platinum plus 2. For the D9, it is copper plus 2. For the D10, it is zinc plus 2. These are the examples. Okay. So, in this way, the crystal field splitting of the octahedral complexes are being explained.